the complexity classes RP and coRP allow one-sided errors to be made, false negatives and false positives respectively. The complexity class BPP allows two-sided errors to be made. What we are left with is the question whether it's possible to use randomization in such a way that our algorithm, our probabilistic algorithm, does not produce any error at all. So it never returns an incorrect result. That seems almost impossible, but there's a slight trick we can use to make this happen. And this is captured in the complexity class called ZPP, which stands for Zero Error Probabilistic Polynomial Time. And what we are doing here is we are allowing the Turing machine or the algorithm to return three different things. So it can either accept the input, or it can reject the input, or it can indicate that it isn't sure. It can say, I don't know what the result is. And by doing this, we allow some wiggle room where the algorithm might not commit to a definite answer. This might be preferable to just giving an incorrect answer, because while you don't get the answer you wanted, a clear accept or clear reject, so you don't know for sure whether the word is in the language or not, at least you know that some kind of problem occurred and that the result is unreliable. So here's the definition of the class ZPP. A language L is in the class ZPP if there exists a Turing machine M and polynomials T and P such that for every input X, the Turing machine M terminates after at most T of X many steps. So this just means the Turing machine runs in polynomial time. And then if the word X is in the language L, then the probability that the machine accepts X combined with a random bit string T, or returns I don't know on such an input, should be equal to 1. So this should always happen, either accept or say I don't know. If the word is not in the language, however, the machine should always, with probability 1, it should always either reject or say I don't know. Now these two conditions alone are not enough, because probabilistic Turing machine that would always return I don't know on any input, it clearly doesn't tell us anything useful. The output would always be I have no idea. And it would satisfy all of these conditions because it would run in constant time, and it also would, if the word is in the language, return accept or don't know with probability 1 because it always returns I don't know. And if the word is not in the language, the same thing. It would always return I don't know, so the second condition is also satisfied. We need something in addition to what we already wrote down. And this is we need to require that the probability that the machine says I don't know has to be bounded somehow. So we require that the probability that the machine says I don't know should be at most 1/2. As before, the choice of this value 1/2 is somewhat arbitrary. You can replace this with any other constant, and we can use, again, probability amplification tricks to get this error probability, where error in this case means the machine says I don't know, as small as you like. As before, we are interested in the relationship of the complexity class ZPP to other classes. And as before, clearly the complexity class P is contained in the class ZPP. And also observe that ZPP is a symmetric language. It treats words in the language and words not in the language in the same way. So ZPP is equal to its complement class, which is coZPP. So ZPP is equal to coZPP. Next, we want to look at the relationship between ZPP and RP and ZPP and coRP. And this relationship is very interesting. Let's again write down what ZPP means. A language L is in ZPP if there exists a polynomial time Turing machine M1 such that if a word is in the language, the machine accepts or says I don't know with probability 1. And if a word is not in the language, the machine rejects or says, I don't know, with probability 1. And it only says, I don't know, with the probability of at most 1/2. Okay, now remember what the class RPP asks for. A language L is in the class RPP if there exists a polynomial time Turing machine M2, such that if a word is in the language, then the probability that M2 accepts should be at least 1/2. But if a word is not in the language, then the machine should reject for sure. Okay, so now we can turn a Turing machine M1 into a Turing machine M2. How do we do this? Maybe pause for a minute and think about it, and then I will tell you the answer. The main problem here is that the answer I don't know is not allowed for this Turing machine of type M2. So what could we possibly do? If we run machine M1, we might get this answer I don't know, but this is not an allowed answer anymore. But the trick is easy. Whenever the machine M1 returns I don't know, we simply reject instead. And if you think about it, what this means is that if a word is not in the language, we will reject for sure. But if a word is in the language, then we will either accept or say, I don't know in M1, and this I don't know will be turned into a reject. So we will either accept or reject. That doesn't seem very helpful, but remember that we only say I don't know with the probability of at most 1/2. So therefore, if a word is in the language, our new machine would only reject with the probability of at most 1/2, which means it has to accept with a probability at least 1/2. This demonstrates that if a language is in the class ZPP, the language is actually also in the class RPP, because we can turn this Turing machine M1 into a Turing machine M2. And therefore, ZPP is contained as a class in RP. Exactly the same argument works for CoRP, of course. The only difference is that now if we transform our Turing machine, we replace outputs of I don't know with accept. And that demonstrates that ZPP is also contained in CoRP. So ZPP is contained in RP, and it is contained in CoRP as well, which means that ZPP is contained in the intersection of RP and CoRP. Here's the really nice part though. ZPP is not just contained in RP intersect CoRP. ZPP is actually equal to the intersection of RP and CoRP. And to see this, we will now show that ZPP is a superset of RP intersect CoRP. To see this, assume that you have a language that is contained in RP and is also contained in CoRP. This means that there exists a polynomial time Turing machine M2, such that if the word is in the language, the probability of this machine M2 accepting the word is at least 1/2, and if the word is not in the language, the machine will reject for sure. And because the language is also in CoRP, it means there exists a polynomial time Turing machine M3, such that if a word is in the language, M3 accepts with probability 1, so for sure, and if the word is not in the language, the machine rejects with probability at least 1/2. So we have both of those machines if we know that the language L is an RP intersect CoRP. And what I'm claiming is that if we have both of those machines, we can construct a new machine, M1, which satisfies all the conditions for the class ZPP. So it will run in polynomial time. It will always say accept or I don't know if the word is in the language. It will always reject or say I don't know if the word is not in the language. And it will only say I don't know with probability at most 1/2. It would be a good exercise for you to try to construct such a machine M1 yourself. Why don't you try that? And then I'm going to tell you how it works. Our new machine M1 does the following. It runs the machine M2, and if M2 accepts, it accepts. And that's it. If M2 does not accept, meaning it rejects, then we run the machine M3. And if M3 rejects, we reject. And if M3 does not reject but accepts, then we report, I don't know, I didn't come to a definite conclusion. I claim that this machine never gives the incorrect answer, meaning if it accepts, the word must be in the language. If it rejects, the word is certainly not in the language. And I also claim that this machine M1 will only say I don't know with a probability of at most 1/2. So first let's argue that the machine M1 never gives an incorrect result. So if it accepts, the word is really in the language. If it rejects, it's really not in the language. If the machine accepts, it means that this machine M2 must have accepted the input. But the machine M2 only accepts the input if the word is in the language. Otherwise, it rejects for sure. And therefore, this must always be the correct answer in this case. On the other hand, if we report reject, then it must have happened that the machine M3 rejects the input. And we know this only happens if the word really is not in the language. Otherwise, we know that the machine M3 will accept for sure. So in both of those cases, we always get the correct result. And then the only other result we can get is an I don't know, which is certainly not incorrect, although it's also not super helpful, of course. So the last step is to say that this unhelpful answer of I don't know doesn't occur too frequently, meaning the probability that it happens is only at most 1/2. So let's go through the steps again of this machine M1 that we constructed. If the word is in the language, then the machine actually stops after the first step. Because if the word is in the language and we run machine M2, then that machine accepts with a probability of at least 1/2. And in that case, we terminate at this point. If the word is not in the language, then we don't get past the second step of the machine. Because if we run M3 and the word is not in the language, then M3 will reject with probability of at least 1/2. And that means we terminate at this point. So if the word is in the language, we don't get past the first step with probability at least 1/2. If the word is not in the language, we don't get past the second step with probability at least 1/2. And so we can only reach the third step in either case of this machine M1 if neither of those previous things happen, and therefore this has to be bounded by a probability of 1/2. This shows that RP intersect coRP is contained in ZPP, and we've discussed before that ZPP is also contained in RP intersect coRP, and therefore ZPP is actually equal to RP intersect coRP. This is a bit different than what we had with NP, coNP, and P. If you remember, we look at the intersection of NP and coNP, and we know that P is contained in this intersection, but it is not known whether P is equal to that intersection. But for these randomized classes, we have that sort of relationship. So RP intersect coRP is actually exactly equal ZPP. So it gives us a nice characterization of the class ZPP. Finally, there's yet another way we can look at the class ZPP. So you might be unhappy with this idea of getting an I don't know as a response. What about if you don't want any errors at all in your probabilistic algorithm? But you also don't want to allow a response of I don't know. So you always want to get a specific answer, accept or reject, and you don't want any errors involved. And this is possible, although maybe that's surprising at first. We just have to rethink a little bit of what we believe the randomization influences. So far, the randomization that we introduced into our algorithms always influenced the result of that algorithm. So whether we accept or reject, or in these weird cases, we respond with I don't know. It does not have to be this way, though. We can also allow the algorithm's runtime to be influenced by the random bits. So basically, we have this alternative definition of the class ZPP that looks like this. A language L is contained in ZPP if there exists a zero-error Turing machine, M prime, that runs in expected polynomial time. So we do no longer require that the machine runs in polynomial time guaranteed on every input. What we do require is that on any input, the machine runs in expected polynomial time. I claim that this definition is equivalent to the definition we had before. To see this, we want to transform a machine that satisfies the definition from before into such a machine M prime that always gives the response, but whose running time is now only polynomial in expectation. How could we construct something like this? Well, suppose we just run this machine M, and there's some chance that the machine will say, I don't know. What do we do if we get such a response? We just run the machine again. And then we have some chance of getting I don't know again, in which case we run the machine a third time, and so on. We just run the machine however many times we need until we get a accept or reject decision. It is clear that this newly constructed machine will never give an incorrect answer, and it's also clear by construction that it will never say I don't know. The only question is, what is the running time of this machine in expectation? So how often do we rerun this machine M in expectation until we get a definite response that is different from I don't know? Because the machine M will only say I don't know with a probability of at most 1/2, in expectation we only need to run it twice to get a definite answer. So the running time of our new machine is in expectation twice the running time of this machine M. And because the machine M did run in polynomial time, the newly constructed machine also runs in polynomial time. What about the other direction, though? Suppose we have a machine that always gives an answer but only runs in expected polynomial time. How can we transform such a machine into one that runs in guaranteed polynomial time deterministically, but sometimes with a probability of at most 1/2 is allowed to give a response of I don't know? The main idea for this is to take the machine that runs in expected polynomial time and run it for a polynomial number of steps. And after that, we abort. If we got a response before this abort occurs, we have our answer. If we did not get a response until then, and the machine would still continue running because it hasn't found the answer yet, we simply report, I don't know. Clearly this runs only in polynomial time, and clearly it never gives the wrong answer. The only question is whether the response, I don't know, is really only given with a probability of at most 1/2. And for this, we need to choose the time at which we abort carefully. I said we want to run the machine for a polynomial number of steps, but that's rather imprecise. We need to really be specific here and think about for how long exactly we want to run the machine. And to determine how long this should be, it is useful to know what's known as Markov's inequality. Markov's inequality states that if x is a non-negative random variable and c is a positive constant, then the probability that x is at least c times the expected value of x is at most 1 over c. Markov's inequality should be fairly intuitive. Let's say c is equal to 2. Now, imagine, for example, you live in a country where the average salary is £30,000. Then not more than half the population could possibly earn more than £60,000. Because if this were the case, then even if everybody else earned nothing at all, the average would already be greater than £30,000. Markov's inequality simply formalizes this idea. We can now apply this to our situation. We have an algorithm that runs an expected polynomial time. And what is the probability that this algorithm will run for twice as long as its expectation? The probability of that must be bounded by 1/2. So therefore, if we abort running this algorithm after 2 times its expected running time, then we will only abort with a probability of at most 1/2. So this tells us for how long we have to run this Turing machine M prime. We look at what the expected running time of the Turing machine is, which is some polynomial function, and then we run it for twice as long. And if we do that and only abort after that and then return I don't know if we reach that point, we know that we only return I don't know with a probability of at most 1/2. It's a simple consequence of Markov's inequality.